In this lab, we're going to look at some reactions involving salt solutions, as well as the properties of said salt solutions. In this first part of the lab, we're going to combine some salt solutions and look for the formation of precipitates. So basically, I'm going to add a couple of drops of each solution into this sort of well plate, and so you can see the reaction that happens, or in some cases doesn't happen, inside these wells. Okay, so with the dark background of the benchtop, hopefully if any precipitates form, you'll be able to see them. Alright, first up we have silver nitrate and sodium chloride. So I've added a couple of drops of silver nitrate to this first cell over here. So remember, silver nitrate is AgNO3. Oops, that's going to show up very well there. There we go. And we'll now add our sodium chloride to that, so I'll get a few drops of that. Okay, and hopefully that should be pretty clear as to what happened there. You can see this, it's turned white and cloudy, so it's clear evidence of a white precipitate. This test should look pretty familiar to you if you remember this is a test for chloride. Silver nitrate forms silver chloride with any chloride ions present. So your sodium chloride provides those chloride ions and forms that precipitate of silver chloride, which you can see. Alright, next up we have our silver nitrate with sodium sulfate, Na2SO4. So let's go ahead and grab a couple of drops of that. And let's put that in this well over here. Oops. Okay, so I've already got some silver nitrate in this cell over here. So let's add some sodium sulfate to that. Oh, and there we go. Alright, our third trial involving silver nitrate involves us adding some sodium phosphate to that. So let's go ahead and add that to this third cell over here. Okay, and hopefully that should be pretty clear as well. Okay, these next three trials are going to involve calcium nitrate over here. Hopefully that'll show up in focus. There we go. Calcium nitrate. And so I've gone ahead and added it to 3 cells, just like I did with my silver nitrate. So first up, we're going to react our calcium nitrate with sodium chloride. So let's take a couple of drops of our sodium chloride here and observe what happens with our calcium nitrate. Okay, so again, if it turned cloudy, make a note of that, and if not, that tells you that there's no precipitate forming. Alright, for this one we're going to take our calcium nitrate and add a few drops of sodium sulfate. Alright, so let's go ahead and add that in there. So we'll do that in this cell over here. Alright, so hopefully you'll be able to tell whether or not a precipitate formed. And for our last trial, we're going to take our calcium nitrate and add a few drops of sodium phosphate to that. Okay, so let's go ahead and do that now. Okay, we'll add that to this last cell over here. Here are some stills of the individual cells, just in case it took a little while for some of the precipitates to show up. All right, so let's walk through how we're going to fill out this part of the lab report.
So essentially what we want to do in this section of the lab is we want to look at how mixing together two solutions of two different salts, two different ionic compounds, may cause a double replacement reaction to happen when one of your products is an insoluble salt, a precipitate. Right? So we observe this in the actual lab when we see the solution go cloudy. That cloudiness that we see is the insoluble product. Okay, basically we're setting up a double replacement reaction in all of the things we're trying. So all of the six combinations that we're doing here um, essentially allow for a double replacement reaction where the cation for one reactant pairs up with the anion of the other, and the cation of the second reactant pairs up with the anion of the first reactant. So you can see that what we're doing here in this column of this table is just to make it easier to see those pairings. Okay, so essentially what we're doing on the top row over here is we're taking that first reactant and we're splitting it into the ions that make it up. So silver nitrate splits up into a silver ion. Now a silver ion has a +1 charge, which hopefully you've memorized. Even though it's a transition metal like zinc, silver has a set charge. You don't need a Roman numeral for it. So silver is always +1. Okay, so we represent that with the symbol Ag and its positive charge in the top right corner. Likewise, nitrate is a polyatomic ion, NO3, with a -1 charge. That's the formula of nitrate. And that's why the formula of silver nitrate is AgNO3. You just have that plus charge and that negative charge canceling each other out to make this formula. But when this is dissolved in solution, these two sets of ions are floating around freely. Okay, so we're writing these two separate ions out here. Down here we have sodium and chloride from our sodium chloride. So we take our sodium ion, which sodium's in group 1, so it has a +1 charge. Chloride is in group 17, so it has a -1 charge. Right? It's one away from the noble gases, so a chlorine atom would gain an electron to become chlorine with a -1 charge, or chloride. And that's the pair of ions we get from sodium chloride. Now, in the double replacement reaction, we sort of cross these two. So the silver ion pairs up with chloride, and sodium pairs up with nitrate. Now, of course, when we see this reaction, and you've seen this in multiple labs, of course, we're going to get that white precipitate, right? So just to put down our observations here, we see a white precipitate. Okay, you could just write PPT if you don't want to write out the full word precipitate. Okay. So we see a white precipitate. Now, what is that white precipitate? Well, it can't be sodium nitrate, because hopefully if you recognize your solubility rules, which you'll see in chapter 11, but if you haven't seen that video yet, you'll know that, just know that all sodium salts, all group 1 metal salts, sodium, potassium, etc., are going to be water soluble. So you'll never get a precipitate that has a sodium ion or a potassium ion in it. Okay. Conversely, all nitrate salts are also soluble. You'll never get a precipitate that has nitrate in it, for that matter. So sodium nitrate, there's a double whammy. There's definitely no way that's your precipitate that you're seeing. Okay. So it's clear that the white precipitate must be the silver chloride that we're seeing. So we're going to write out the formula for that over here. And so the formula is just AgCl. Okay, and we know that that's the formula because if silver has a +1 charge and chloride has a -1 charge, we need to balance those out with just one silver ion and one chloride ion. Again, this is going back to chapter 5, learning how to balance out charges to write our ionic compound. Okay, so we're going to keep that up in all of our, in the rest of this table. Okay, so you're going to go back through the video, and I've taken some stills there to make this a little bit easier for you. But you're going to see if the reaction between any two pairs of ionic compounds gives you a precipitate or not. Okay? If there isn't a precipitate, if it stays clear, then just leave this column blank. Okay? There is no insoluble salt. So they only want the formula of the insoluble salt. Okay, so definitely don't include anything with a sodium ion or a nitrate ion in this column. Okay. So let's try one more problem out. Let me walk through the second example with you, just so you can see what this is like. Okay, I'll let you do the rest of the table yourselves, but let's at least use this second example as a working example so you can kind of follow along. Okay, and I kind of like this one because here we have an ion that doesn't have a plus, just a +1 or plus minus or -1 charge in sulfate, which has a -2 charge. So let's try this out. We have our silver nitrate again. So just like over here, we have our silver ions, Ag+, okay, and our nitrate ions, which are NO3-, okay, which hopefully memorize, but if not, that's okay. You can look that up and see that that's nitrate, though if you know that silver is +1 and there's only nitrate, there's no parentheses around a number outside, you know that it must be a -1 to balance that out. Okay, so nitrate's NO3-, it's going to be the same in all of these. Likewise, sodium, in our sodium sulfate, well, sodium has to have a +1 charge. The formula of sodium is Na+. Okay, please don't put the 2 down here. That 2 is not part of the formula of sodium. Sodium is not a polyatomic ion. It's one element. So you don't need a 2 over there. Okay, we're going to see why we need that 2 in a second. What's the formula of sulfate? Well, sulfate's a polyatomic ion, and it is SO4, okay, with a 2- charge. Now, because this is a 2- charge, and that's a +1 charge, that's why we needed 2 sodiums to balance that out, okay? But that 2 is not part of the formula of sodium, and so we didn't include that here. We have to include the 4 for sulfate because that is part of the formula of sulfate. Sulfate is a polyatomic ion with sulfur and oxygen, with 1 sulfur and 4 oxygens, and that is its formula. If we had only 3 oxygens here, it wouldn't be sulfate, it'd be sulfite. Okay, so again, it's very important you get these ions correct over here. Now, what are our 2 combinations of products? Well, our sodium will pair up with nitrate, of course, but our other combination is silver and sulfate. Okay, so go back to that video and see what, first of all, see whether you had a precipitate or not. We want to write down this observation here. Okay, so if you have gone back to the video and come back here, or just remember, we had a white precipitate as well when we mixed together our sodium nitrate, or silver nitrate and sodium sulfate. So that white precipitate that we see must have been our silver sulfate. It definitely couldn't be our sodium nitrate. I've already explained why that can't be a precipitate ever. So the silver sulfate must be the precipitate that we saw. So we want to write down the formula of that precipitate, that insoluble salt that we've created. So what is the formula when silver pairs up with sulfate? Well, if silver has a +1 charge and sulfate has a 2- charge, that means that we're going to need 2 silver ions, 2 positive charges, to balance out the 2 negative charges on our 1 sulfate. So when we write out that formula, we have to put a subscript of 2 next to our silver. Okay? So there's the formula of silver sulfate. It's Ag2SO4 to balance out those charges. Okay, again, if you need more practice on this, we cover this back in chapter 5 when we look at balancing the formulas of ionic compounds. Okay, so let's take this information and work on this part of the problem. We now want to write out ionic and net ionic equations representing what's happening in our complete balanced equation. So we actually have to start off by writing out a balanced equation where we show the products of this double replacement reaction. Again, this table up here helps us with that. We are pairing up our 2 combinations. So, in this example, our products are going to be silver chloride and sodium nitrate. In this example here, our products are going to be silver sulfate and sodium nitrate. Okay, so we're going to write those on the product side here. Now, the thing you've got to watch out for is you need to balance out your equation. This first example is kind of, doesn't really show you that because it turns out that everything winds up being balanced. I'm not going to walk that through this with you because, to be honest with you, the pre-lab actually does this for us. If you go back to your pre-lab, Okay, you can see here they actually give you the answer to that first problem. They show you how you write out the products of your of your double replacement reaction. Again, they point out that silver chloride is a solid. Notice that everything else has the state symbol aqueous, okay, because they are soluble in water. It's the silver chloride that is not, that forms that white precipitate. So we then have to write out an ionic equation and a net ionic equation. To write out an ionic equation, any of your compounds that are aqueous should be split up into their ions. So for example, silver nitrate gets split up into silver ions and nitrate ions. Okay? We show this kind of represent what these compounds look like in water. When they're in solution, those ions are no longer stuck together in a crystal, but they are separate and free, floating around the solution. And so the ionic equation kind of shows us that. It shows us what ions are floating around in solution. Okay, so again, anything that has that AQ after it as its state symbol, that's going to be split up into its ions. Okay, so sodium gets split up into sodium ions and chloride ions. We leave silver chloride alone; it stays a solid. Okay, so it doesn't separate into its free ions because it's insoluble. It stays together in a crystal. Our sodium nitrate, on the other hand, is aqueous, so it splits up into sodium ions and nitrate ions. Okay, so everything that's aqueous, every ionic compound that's aqueous splits into a cation and an anion, something positive, something negative. Now, the last step in this is you've got to write out the net ionic equation. To do this, you look at your ionic equation and ask yourself, what are my spectator ions? Spectator ions are ions that exist on both sides of the equation. They stay ions, they stay free ions that are aqueous. In other words, they don't change, they don't do anything during the reaction, right? They're kind of like spectators at a sporting event. They're watching the game, they're watching the match, but they're not playing the sport. They're just there to watch. They're just there. They're part of the environment, but they're not actually doing anything other than watching. Spectator ions, in this case, do the same thing. For example, notice that we have a sodium ion over here, Na+, and it's still Na+ aqueous on the product side as well as the reactant side. Okay, so you could kind of think of it as canceling out. The Na+ on the left cancels out with the Na+ on the right of that arrow. Similarly, we have nitrate. Nitrate is NO3- aqueous on the left-hand side, and it's NO3- aqueous on the right-hand side, so it also cancels out. So what is left? That is your net ionic equation. So Ag plus Cl minus gives us AgCl, our solid, our precipitate. Okay. Notice that silver and chloride do not cancel out because they are not the same on both sides. Obviously, you have the elements silver and chlorine involved, but they're not in the same form. On the left, we have free ions, so we have Ag plus, that's aqueous, and we have Cl minus, that's aqueous. But on the right, they are trapped together in that precipitate, which is a solid. Okay, and that's why they don't cancel out when we're taking out our spectator ions. Okay, so that's what we do for the net ionic equation. We write out that what's left over from our ionic equation when we remove our spectator ions. Little quick shortcut here, if you ever see this on a quiz or exam. Whenever you have a precipitation double replacement reaction like this, and you're trying to write out your net ionic equation, the quote-unquote product of your net ionic equation is always the precipitate you're trying to form. Okay, and the quote-unquote reactants are actually the ions that make that up. Okay, so that's probably a great way to check your work. If for any of these, when you do have a precipitate, your final net ionic equation should only have this precipitate on the product side. Okay, so let's try this out with our second problem as a kind of little check for us. Again, I want to illustrate what happens when you don't have a simply balanced equation. That first example was really straightforward because everything had either a +1 or a -1 charge. So we didn't really actually have to balance anything. The equation was already really balanced. Okay, so let's try the second example out, just so we can see what happens when we actually have to balance the equation. So let's start out by writing out the products of this complete balanced equation. So we are pairing up our, if I go back here, you can see that our sodium and nitrate pair up, and our silver and sulfate pair up, right? So we've already seen that the formula of silver sulfate is Ag2SO4. So I'll go ahead and write that out. Okay, so we've got Ag2SO4. And as we've seen, that's our precipitate. That's going to have a state symbol of S for solid. This is not dissolved in water. This is the white cloudy stuff we see in the lab. Now, what's the other product that we make? Well, we have sodium nitrate. What's the formula of sodium nitrate? Sodium has a +1 charge. Nitrate has a -1 charge. So sodium nitrate is just NaNO3. Okay, it's the same product, the same formula that we're going to have in this equation as well. So if we go back to that problem, you'll see that the formula is still NaNO3. Okay, don't panic over the fact that there's a 2 over here. We're going to take care of that in a second. But it's before we start balancing the whole equation, let's get the formulas right based on the charges. If Na has a +1 charge, so we can see over here, and nitrate has a -1 charge, we only need one of each of those ions to balance each other out. Okay, so the formula is NaNO3. And if you want to put state symbols, that's also going to be aqueous. Right? As I pointed out, any sodium salt, any nitrate salt will always dissolve in water, and therefore it's going to be aqueous here. Okay, that's its state symbol. All right, we're not done though, because as I pointed out, you're right, there are 2 sodiums here on the left. There is only 1 sodium here. This is not a balanced equation. As you can see, there's 2 silver ions here and only 1 silver ion here as well. So we need to balance this whole equation. So don't move on in this problem until you balance this, because if you don't balance this equation, you're probably going to make mistakes in these next 2 steps. So let's try balancing this. Well, as I pointed out, there's 2 silver ions over here. So let's put a 2 over here. Okay, so now we have 2 silver ions on the left, 2 silver ions on the right. But by multiplying this by 2, that means we also have 2 nitrates. So let's double the number of sodium nitrates. Now we have 2 nitrate ions on both sides of the equation. But this means we have 2 sodium ions on the right. Well, good news, we have 2 sodium ions on the left, and since we have 1 sulfate on both sides, this is a balanced equation now. Okay, so those 2's that you've got to put over here to balance this equation are kind of important. Please keep that in mind when you're balancing the rest of these equations. I really recommend not moving on to the ionic equation, net ionic equation, without first making sure that this equation is balanced. Okay, and I recommend not even attempting to balance the equation until you get the formulas of your compounds right. Okay, if we had named this as Na2NO3, which is not the formula of sodium nitrate, we wouldn't have been able to balance this equation properly. Okay, so always look at the charges of your ions when you're trying to balance out the formula of your ionic compound. Okay, all right, so let's move on to our ionic and net ionic equation. As I pointed out earlier, anything that's got an AQ next to it, okay, so in other words, everything except your precipitate, needs to be split up into its ions. All right, so let's ignore this 2 for now. Let's look at just silver nitrate. What are the ions in silver nitrate? And again, if you want to look up here, this as a reminder, remember, silver has Ag plus and nitrate is NO3 minus. Those are the ions that we get from our silver nitrate. So let's write that over here. We have Ag plus NO3 minus. These are going to be aqueous. Just to save some space, I'm not going to write out the state symbols for anything that's aqueous, just to save some room here, okay? Now let's worry about that 2. If 1 Ag plus splits up into 1 silver ion and 1 nitrate ion, how many of these ions are we going to get if we have 2 silver nitrates, 2 AgNO3s? Well, we're going to get 2 of each of them, right? So our 2 silver nitrates will give us 2 silver ions and 2 nitrate ions. Okay, so we because we're doubling the number of silver nitrates, we're doubling the number of ions that come from that silver nitrate. Okay, now let's have a look at our sodium sulfate over here. Again, that's aqueous, so we're still going to break that up. We can see that that splits into sodium ions and sulfate ions. Sodium has the formula Na+, sulfate has the formula SO4 with a 2- charge. So let's again write out the formulas of those ions. We have Na+. Okay, again, I'm just only writing the symbol and charge for sodium. I'll worry about the number of sodiums in a little bit. And then, of course, sulfate, as we've seen, is SO4 with a 2- charge. Okay, now looking at sodium sulfate, as I pointed out, there are 2 sodium ions in this formula. So since this is separating out into separate ions, and sodium is not a polyatomic ion, these sodiums are not going to be stuck to each other through a covalent bond when this dissolves in water. So these sodium ions are going to be separate and free. So the 2 sodium ions that are attached to your sulfate ion here are 2 separate sodium ions. So we've got to write a 2 in front here for that. Sulfate stays SO4 2-. That 4 doesn't come out in front because those 4 oxygens are covalently bonded to that sulfur. This polyatomic ion of sulfate stays SO4 2-. And there's only one of it. If there was more than one of it, you would see parentheses around it and a number, kind of like nitrate in calcium nitrate. Okay, there's 2 nitrates in calcium nitrate. That's why there's parentheses around our NO3 and a 2 over there. Okay, let's move on. Next compound. Now here we have silver sulfate. What ions does that split up into? Trick question, it doesn't, right? That's a solid. So we just write that as Ag2SO4. Okay, that one's nice and easy. Just write it out the exact same way. Okay, and then what about sodium nitrate? What does that split up into? As we pointed out earlier, it's going to split up into sodium ions, Na+, and nitrate ions, NO3-. Okay, but of course, since each sodium nitrate does that, each NaNO3 gives us 1 Na+ and 1 NO3-, if we have 2 sodium nitrates, we have to double those numbers. 2 sodium ions and 2 nitrate ions. And there's our ionic equation. Phew, that was long, right? Ionic equations take a little while, and so this is going to be a little tedious, but the reason we do this is so that you get lots of practice at this, okay? So it seems long and clunky, and trust me, from a professor's perspective, it's not fun to grade, but it is really important you practice this, okay? It'll get easier the more and more you practice this. Okay, let's move on to our net ionic equation. What are our spectator ions in this problem? Well, they're going to be the same as we saw in that earlier example. Notice that we have 2 nitrate ions over here, and we have 2 nitrate ions over here. Those are going to cancel out. Likewise, our 2 sodium ions over here and our 2 sodium ions over here are going to cancel out. So if we ignore sodium and nitrate, we have 2 Ag+, okay, just reading this from left to right from our ionic equation. So our 2 Ag+ comes down here, and we have our sulfate ion. Okay, it's because we skip nitrate, we skip sodium, we go to sulfate. SO4, SO4, 2-. Okay, and then arrow. And then we have Ag2SO4, that's our solid, so that's going to show up there. Okay, again, I left out state symbols just to make this a little bit easier to see, but I guess I can put them down here since I've got some room. So remember, silver ions are aqueous. Okay, and our sulfate ions are also aqueous. And our silver 2-sulfate is a solid. Okay, and you can see that this is still a balanced equation, right? We have our 2 silver ions pairing up with our sulfate ion with its -2 charge. So the charges cancel out, and we wind up with our neutral silver sulfate. And again, that has 2 silvers in it and 1 sulfate. So this is still a completely balanced equation, even though it has ions in it. Okay, so that's how you write out an ionic and net ionic equation. So be sure to do that for the rest of these as well. Okay. Now, a quick point here. You'll probably notice that one of the trials we did, one of the combinations, stayed clear. It didn't form a precipitate. Okay. So again, in this table, please note this last column only needs the formula of the insoluble salt. Okay. If there is no precipitate, if your mixture stays clear because you didn't form a solid product, you leave that example, you leave that cell over here, that field blank for whichever one that is. Okay, I'll let you go back through the results and figure that out. Okay, now how does that affect an ionic and a net ionic equation? Well, remember, anything that's aqueous gets split up into its ions. So if this were not a solid, this would also have been split up into silver ions and sulfate ions. Okay, so in the case of your combination that doesn't have precipitate, you're going to have everything aqueous, which means everything gets split up into its ions. Well, if this were not a solid, if this were aqueous, and these were just silver ions and these were sulfate ions, would they cancel out with the silver ions and sulfate ions here? Would they also be spectator ions? And the answer is yes. So when you don't have a precipitate, it turns out that everything winds up being a spectator ion. So you write out your ionic equation, but there won't be a solid that stays intact. It will also be split up into its ions the same way your ions on your reactant side were. Okay, and since since everything's a spectator ion, everything cancels out, your net ionic equation field would be blank. Okay, so the only reason we have a net ionic equation is because we have a precipitate, because one of our products is a solid, that we're able to do this. Okay, so when for the example here, for the out of the remaining 4 questions, one of these doesn't produce a precipitate, you're not going to have a net ionic equation for that. Okay, though please, of course, you still have to write out the ionic equation for that, so don't forget to do that. Okay, so good luck with that, and let's move on with the lab.
In the next part of this lab, we're going to draw a solubility curve for potassium nitrate. Now, ordinarily, you plot solubility versus temperature by seeing what the solubility values are at various temperatures. We're going to do this lab a little bit backwards. We're going to measure out potassium nitrate and figure out at what temperature that amount of potassium nitrate would make a solution saturated. So we're basically going to take our potassium nitrate, dissolve in 5 milliliters of water, and then just see at what temperature, as it cools down, it crashes out of solution. Okay, because that's the point at which your solution is saturated, where it just crashes out. So we're going to take various amounts of potassium nitrate. I'm going to demonstrate this with one run, and then I will provide you with some other student data. This is how we'd actually run this if you were here present in lab. Typically, we do this as a group experiment where different lab pairings each do a trial run, and we pool everyone's data together. All right, so let's start off by getting our mass of potassium nitrate for our trial. Now, your directions say to get the mass of your container as well as your the mass of the container plus potassium nitrate, and then you subtract the difference. We're going to simplify things a little bit since we're the only ones using this mass balance here. I'm just going to go ahead and tear our container. So let's tear that. Oops, there we go. All right, so we're going to go ahead and add our set amount of potassium nitrate here. So there's our mass of potassium nitrate. Alright, so now we'll add our potassium nitrate very carefully to this test tube. It might be easier if I hold this in my hand while I do that. There we go. You can see that alright. Very careful to make sure I get all of the potassium nitrate we had in our weight boat here into our test tube. Alright. Let's keep that ready here. Okay. Now, to make sure that we have exactly 5 milliliters of water that we're going to add to this test tube, we're going to use a pipette. Our pipette here has markings on the side, and this pipette specifically is designed to measure out exactly 5 milliliters of water. So we're going to use a pipette bulb here and attach it to our pipette. Here so you can see what I'm doing. So here I have a beaker of distilled water. So you can treat your pipette bulb kind of like a syringe. You can pull up on this plunger over here, basically just like a syringe, and that sucks up water into the pipette like a straw, or well, like a syringe would. Now, if you want to have a little bit more control over things, basically you can use this little wheel over here, and that also raises the plunger of your pipette. Okay, and I don't know if you guys can see this very well. Maybe if I pull this a little bit closer, you can see that as I draw the wheel, I'm basically drawing water up into the pipette. Now, I want to try and get this to the 0 mark on my pipette there. Now, I'm going to have a little trouble trying to get that exactly right, and I'm sorry if this is a little bit hard for you guys to see with that going in and out of focus, but basically, it's going to be hard to get this exactly where I want it. Actually, that's pretty close, but we can do better. So the way I'm going to do this actually is to use my hand and do this manually. So I'm going to pull this actually past the mark. I'm going to avoid pulling all of the water up into the pipette bulb itself, but I'll pull it up here. And what I'm going to do now is very carefully, I'm going to have my hand ready, and I'm going to clamp my thumb on top of the pipette bulb, the pipette opening, and air pressure will basically keep the water level more or less steady. So you got to get ready. You have my thumb ready to cover this. I'm going to pull my pipette bulb straight up. You want to be careful not to pull it to the side, or you don't want to break the glass. So pull that up and immediately put my thumb on this opening here.
All right, so I noticed two things. One, it's hard to show this while handling the webcam, especially it's poor focusing. So I'm using my phone here. Secondly, I noticed that I was able to get a better seal on the pipette with an ungloved hand, so I decided I'd take off the gloves there to show that to you. So, as you can see here, I've gone past the 0 with my pipette bulb, or with my pipette, and so I'm just going to gently ease up on my thumb there, and that will let the water level drop as it lets water out of the pipette. You can see if I just gently either there let drop water drip out drop by drop. Okay, so we're just going to very slowly let it drip out and keep an eye on that while reading that lower meniscus. Then when it gets to 0, clamp down. And there you can see, hopefully, I've reached the 0 point. Okay, and the lower meniscus is touching that line, and therefore I've got 5 milliliters of water in my pipette, which I am now going to add to my potassium nitrate, I'm just going to release my thumb here like that. And you can see all of the water is just draining into my, my test tube with my potassium nitrate. Okay, so we have 5 milliliters of water now in this test tube, as well as our potassium nitrate that we weighed out. So we're going to put this in a warm water bath and get it to dissolve. All right, so once it's all dissolved, we'll take it out of the warm water bath and go from there.
All right, so here you can see our setup for this experiment. I've got a hot plate with a hot water bath sitting here. Basically we're going to take our potassium nitrate. As you can see, it's over there in that test tube still with our 5 milliliters of water. We're going to heat it up using this hot water bath and basically convert it into a solution. And once it's dissolved into a solution, we will take it out of the hot water bath. We'll just raise it up on this clamp stand, and we'll make a note at the temperature at which the crystals crash out of solution. Because at that point, where those crystals just fall out of solution, we'll have a saturated solution. So let's keep an eye on this, and I'm going to stir it with the thermometer, try and get it to dissolve a little bit quicker. And once we've got this dissolved, I'll go ahead and we'll keep an eye on it with the webcam, so you guys can get a temperature reading on that. Okay, I've set up our hot solution here, and it's cooling down, as you can see, with our thermometer there next to it, or at least the readout for our thermometer well next to it. And so keep an eye on the test tube, especially down near the bottom, and see where you can, see if you notice when crystals start appearing. Try and set up a dark background there for you, so hopefully that will make it a little bit easier for you to see the appearance of any crystals. That's something interesting. Notice the little crystals that are there at the bottom. Oh yeah, there we go. See these crashing out of solution. Alrighty, there we go. So make a note of the temperature at which these crystals first appeared. So feel free to rewind the video a little bit to get that temperature. But you can see, there we go. We have crystals crashing out of solution, and that tells us that our solution is now saturated.
Okay, so here we're going to collect some data. I'm going to provide you with some extra data in addition to our own, and we're going to try and plot out a solubility curve for potassium nitrate. Now, we measured the mass of our potassium nitrate directly. Since I was the only person in the lab and I was only doing my trial, I didn't bother, taking the mass of my container and including the mass of potassium nitrate. I think I just recorded that mass. We have 3.363 grams of potassium nitrate. And of course, we can record the temperature at which these crystals first appeared. So, go back and watch the video, rewind to where you first saw those crystals appear. But let's say they appeared at 37.3 degrees. Okay, let's say that's where I saw them appear. Okay, you might not see it exactly that. You might see it 37.2, 37.4. Whatever you saw, make a note of that temperature here. Okay. You don't want to use this mass in your graph. The graph we're going to draw on this next page will include the solubility values of our different solutions of potassium nitrate. So remember, this was the mass, the grams of potassium nitrate that we dissolved in 5 milliliters. Okay, we measured out 5 milliliters of water. So how much did we dissolve how much would we dissolve if we scaled this up to 100 milliliters of water? Well, that would be 20 times this number. So 67.26 grams per 100 milliliters of water. So again, that's probably just multiplying by 20 is the shortcut to doing this. Really, I guess the proper way to do this is divide that by 5 and multiply by 100, but that's effectively multiplying by 20. Anyway, this is just one data point. You can't plot a graph on this, right? So we need more data. I happen to have the data from one of my classes, I think back in the fall of 2015. To be honest with you, I'm not sure why I randomly have to have this data on hand, but it's a good thing I did, because it saved me having to make do several trials of the potassium nitrate experiment. So feel free to take any of these samples, any of these examples here. Also note I've only written down the mass of potassium nitrate and the temperature. So again, you don't need the mass of the container or the mass of the container with potassium nitrate, just the mass of potassium nitrate. And using that, remember, this is the mass, the grams of potassium nitrate in 5 milliliters of water. You need to scale it up and figure out what the solubility is, and accordingly, plot that. Okay, but of course, you don't have to do that for all of these. You can just pick a certain number to fill your table. And again, it doesn't matter. Just pick any of these, that you will. I actually, plotted a graph of these, and I saw that they actually, if I use all the data points, we actually have a pretty good standard deviation. It's like 0.98. That's actually really great. So feel free to, like I said, to take any of these data points. You don't really need the names. I think I kept that up for that group back in 2015, just so we could see whose data was what. But just copy down the mass of potassium nitrate and the temperatures for any of the data points that you randomly choose. Okay, so once you've picked out your 4 data points, of course, like I said, fill them into this table. Put your mass here, put your temperature from that Excel sheet I had up earlier, and of course, do the solubility calculation yourself. Just leave these first 2 columns blank; they're not important. And then you're going to plot those data points into this graph. If you want to do this electronically, you're welcome to. You can do that on Google Sheets and upload your PDF file of that, or if you do this in Excel, you're allowed to do that as well. Or if you just want to plot this by hand and plot the curve yourself, you're totally welcome to. Just make sure you draw a line or curve of best fit. Okay, don't join the points up together. You're not going to get a perfect straight line or perfect curve that way. Okay, so it has to be a line or curve of best fit. From your graph, you are then going to answer these questions. Okay, so all of these questions, with the exception of question 5, all these questions pertain to your graph. So especially my students, when I tell you, you oftentimes don't have to do some of these questions, you do have to do these questions. So questions 2, 3, and 4 are related to your graph, so please answer those at least, okay? And of course, according to, if you're not one of my students, follow your professor's instructions. They might have instructions regarding whether they want you to draw this by hand, or if they prefer having you do it electronically using a spreadsheet program. And likewise, they may require you to answer question 5. You know, so I'll leave it up to individual instructors on how they want to grade that. Okay, but for questions 2, 3, and 4, you're essentially just talking about the graph that you're drawing. Okay, so in the case of questions 3 and 4, you are making readings from your graph, okay, using your line of best fit. Please don't use any actual data points. Use your line to make these readings.